Okay, so 1 is base case might not start with 1. So you might have base case start with 3, start with 2, start with 0, start with 10. It depends on, because last time I already talked about it, depends on what is the smallest number the statement holds. Okay, so for example, the statement only holds for n greater than or equal to 3. Then your base case would be 3 instead of 1. Or like something like this for all even unequal a natural, the smallest even natural clearly is not 1. So you might have a different base case for that. That's first kind of variation. Another kind, which is right here, is what you need to prove is not for all naturals. So you might skip some. Okay? For example, it works for all even natural, or it works for all odd natural. Then your proof is gonna be slightly different, which we'll see an example very soon. Okay, even or odd, that's another one. And there are something like, it's not P of K implies P of K plus 1 anymore. So sometimes it's P of K implies P of K plus 3, or P of K implies P of K plus 2, and so on. That could happen as well, which we'll see example in the future as well. So we'll talk about and another one will be strong induction, which we'll talk about today as well. So those are variations of induction, which I basically chose questions that are more similar to your homework questions. So you'll see, hopefully they can be helpful for your homework questions. So that's variations of induction. Any question before we start the example? Anything? Okay, no question here either. Okay, so let's get started with the first example. It says that prove that 3 to the power of n minus 1 is divisible by 8 for all even n in natural. So you can see that clearly this is not just a regular induction. It's a variation because they're talking about even natural, not just all naturals. Right? So my question is, well, we'll still have 3 different things. You have base case, you have IH, you have inductive step. But the thing is, what is my base case? Yes, n equals to 2, that's correct. Okay, so in this case, our base case will be n equals to 2 because 2 is the smallest even natural. So when n equals to 2, I can compute 3 to the 2 minus 1, which is 9 minus 1, which equals to 8. And this is divisible by 8. Cool, base case is okay. So there's not much change here. It's just, well, we need to check 2 instead of 1 because 1 is clearly not even, right? And now there are some changes in IH as well. Because before, before you just suppose the statement is true for some k in natural. Here it's almost the same, except it's not just for some k in natural. You need to suppose for some even k in natural. Okay, so that's the only difference. So everything else is the same. So suppose or assume 3 to the k minus 1 equals to 8m for some even k in natural and m is an integer. So even is important here, and for some, I think I emphasized it many times, it's always for some, never for all when you make assumption. Okay, your assumption should never, ever be for all, because that's assuming what you need to prove. That's IH. There is not much change either, except you need to emphasize we're assuming for even k. Now my question is, what do I need to prove? Do I prove P of k plus 1 or something else? What do I need to prove? Anyone? Yes.
You need to put here k plus 2.
Why?
Because it's only for even numbers.
Only for even. That's correct. Okay, so that's the main difference here. Since k is an even number, so k plus 1 will be odd, which is not what we need to show. Because we need to prove the next even number. In this case, will be k plus 2. Okay, so what we need to consider is actually when n equals to k plus 2. 3 to the k plus 2 minus 1. Okay, I'm going to emphasize the 2 here. And thus, we can rewrite it as 3 to the k times 3 to the 2 minus 1. Okay, so what do we do now? Yes.
We multiply the induction hypothesis by 3, 9.
Okay, so.
And then in order to convert it to the induction step, we have to add 8.
Okay, so you are saying we write it like this. 3 to the k minus 1, and then add 8. Correct?
Yes.
That's correct. Okay, that's one way of doing it. One way of doing that, because well, we know that there are 9 copies of 3 to the k. Here you only have 1 copy, so we can make everything 9 copies and then balance it out and see what do you need to add or subtract. That's one way. The other way, what is the other way? I'm going to show you both because it's good to know both. Okay? What is the other way of doing it? Yes.
You make it times 9, and you split the 9 into 1 plus 8, and you distribute into the 3 to the power of k.
That's correct. Okay, so you can also write 9 as 8 plus 1 and use distribution. You'll get 8 times 3 to the k plus 3 to the k minus 1. And this is your IH. Either way works. It's just I suggest you be comfortable with both ways because sometimes one works, the other doesn't. So anyway, so let's continue. By IH, I can write this as 9 times 8m plus 8. And I can factor out my 8. I'll get 9m plus 1. What was that? Was it me? Which is divisible by 8? That's for this way. The orange way is the same thing. Times 3 to the k plus 8m, which is 8 times 3 to the k plus 1, which is divisible by 8. My question is there anything missing in my proof? No? When I ask you, you should know there is something missing. Yes. Conclusion? Oh, conclusion's okay. Either you make it or not, you're not gonna lose mark. We talked about even k already. Something is missing. Remember I said whenever you use something, you have to cite it. I used something in my proof, but I never mentioned it. What is it? That's correct. Okay, I used inductive hypothesis in this step, so I have to mention it. Here as well, I used that, so I have to mention it. Okay, this is something that's very easily you're probably gonna forget about it. That's why once you are done, you should always go back and check, because that's what I always do. Once I finish my proof, I always go back. Did I quote everything? Okay, did I cite everything I need? So you should always go back and check and see if you talked about what you used. Clear? Is this clear? And then you can make your conclusion. You can say by principle of mathematical induction, the thing is divisible by 8 for all even naturals. Okay, let's see if there is any question here. Any question here? Online people? Any in-person people? Do you guys hear this? It's very weird. Is it a mic? But the mic is not even on. It's really weird. I don't know why it's closed. Anyway, no question? Yes.
For the second method, do you know how like AM turned into one? Can we just turn that into like one, like whatever we keep at like, I mean,
Oh, that's a typo. It should be M here.
oh,
That's a typo. I don't know how to make it stop. It's really weird.
Maybe you just don't touch the mic if you're
I didn't even touch it.
really.
It's left there and it's not even on.
Amplify your plug out and plug in again.
That's really weird, isn't it?
Before you're doing something like the electron.
I don't know. It's weird. There's nothing. I'm not even touching anything. Anyway, let's move on. Let's talk about one of the most popular topic in induction, which is Fibonacci number. Why do I say that? Because this is like all-time favorite for professors to test you on Fibonacci numbers because there are so many properties. I don't even know how many. There are like just like a lot of properties of Fibonacci that you prove them using induction. So it's a great practice that you can just search Fibonacci numbers properties and then prove all of them using induction. That's a great practice because I remember there was one of the professor, I don't know if you know Mike Pollock. He's one of the professor, great teacher in a department. When he was coordinating this course, he coordinated twice. Is it if I don't talk, it's not gonna, never mind. When he was coordinating MAT102, he put it on every single assessment that has induction. So every single induction question was Fibonacci numbers. That's how much he liked it. It's a concept that you cannot avoid in math. And in the future, if you take any other math courses that use induction, you might see it again. Like such as 301, usually Fibonacci number will be the first homework. And it's gonna be either an induction or a strong induction question. It's like 102 material as like a review for 102. So something you cannot avoid. And I chose one of the example that does not require strong induction here. So a lot of people think if you have a recursive sequence, such as this. By the way, what's recursive sequence? What's recursion? You guys are in computer science and you're learning in 148 dimension. Yes.
In this case, it's like the next term is dependent on the previous terms.
That's correct. So your term is dependent on the previous terms, either previous one, previous two, or whatever. So those recursive sequences, a lot of people think if you see them, it means you need to use strong induction, which is not true. And here is a counterexample. I can tell you this question is not a strong induction question, it's a regular induction. But we have a recursive sequence. So you'll see why. Okay? So for this question, there is a typo. Add this greater than or equal to 2. It does not work for 1 n equals to 1. So for this question, I'll give you some time to work on it yourself because we did a lot of induction already and you were tested on it as well. So I'll give you some time to work on it. What I want to emphasize or I want to hint you on is for the other induction questions, usually IH is the thing you need to use. As I mentioned before, you assume this, so you can use it later. For questions with recursive sequence, just don't forget you have this to use as well. Okay, the recursive definition is something else you can use. And for such question, it's usually the first thing you use when you do your induction step. So if you're stuck at induction, look at this and think about what can you use with it, and what can you do with it. And a lot of time, for this question specifically, you need to use it twice. That's my hint, and you can give it a try now. Okay, I'm gonna take half of it up, and I'll give you more time to do the rest. Because if I don't, I'm afraid that you're gonna be stuck forever. Let's see if there is any question. No question online, okay? So base case, what's my base case? When n equals to what? 2, that's correct. Question. Let's call this 1. Let's call this 2. Which one do I need to verify? 1 or 2? 2, that's correct. Okay, this is, I ask you because every semester people take this for granted and they try to prove this. This is definition. It's given to you. You don't need to prove it. This is what you need to prove. So for a base case, you need to check this if this is true. So f of 2 plus 1 and then f2 minus 1 minus f2 squared is gonna be f3 times f1 minus f2 squared. f1, f2 are given to you, but f3 is not given to you, but we can use a definition. f3 is f1 plus f2 times f1 minus f2 squared. Here I'm gonna say by definition. And now this is 1 plus 1 times 1 minus 1, which is 1. But I'm not done yet because I need to check this. How do I write 1 as something like this? 1 equals to what? That's correct. 1 equals to minus 1 to the power of 2. So once you reach here, you can say, well, my base case holds. Okay? Common mistake is you plug 2 on both sides and you do both sides. That's assuming what you need to prove. Okay? Do not do that. Now, hypothesis. Assume f of k plus 1, f of k minus 1, minus f of k squared equals to minus 1 to the power of k. For some k in natural, am I down? Yes. K greater than or equal to 2, that's correct. Okay, for k has to be greater than or equal to 2. Cannot be 1 here. Otherwise, it's not defined. Okay, if it's 1, you'll have 1 minus 1, which is f0. f0 is not defined. So we have to be greater than or equal to 2. And now, consider f of k plus 1 plus 1, f k plus 1 minus 1, minus f k plus 1 squared. Okay, let's simplify it. F k plus 2 times f k minus f k plus 1 squared. So this is where a lot of people get stuck. Because while they look at our IH and they look at us, they're like, oh, there's nothing alike. True. which means you cannot use IH directly. And that's why I said, well, when you have a recursive sequence, the recursive definition is what you need to use first. Okay? So recursive definition, this one, we use this one first. Here, I'm gonna change this using my recursive definition. Why? Because if I look at my IH, I can see that there is no fk plus 2. Okay, this is a term I wanted to disappear, right? Because IH has no fk plus 2. So I want it to disappear. In order for it to disappear, I can use my recursive definition. Okay, so let's use it. That's telling me I have f of k plus 1 plus fk. This is by recursive definition. Is this clear? Why I chose to replace this? So you might say, why do I not replace this as well? It's possible I need to, but I'm not sure yet. Why am I not sure? Because, well, there is a fk plus 1 here. So maybe I don't need to do it. I don't know yet, so I need to figure it out later. Now, let me expand it. So I'm gonna have fk squared plus fk plus 1 times fk minus fk plus 1 squared. Now let's do some observation. If you look at, okay, let me highlight them. If you look at this, what we have now, and what I need, which is my IH, you'll see that we have some terms that I need already. Which terms? I have this term. Although the sign is different, but that's okay. Sign we can fix it later. This term is right here already. I have this term right here. This term is multiplied by fk minus 1. Here it's not that, but it's okay. We can fix it. Okay? And I have an extra term here. That's okay. Why? Because this term also is fk plus 1. So I can factor them out. You see, if I factor it out, it's still fk plus 1 multiplied by another term. Well, after I rearrange it, maybe that term is going to be what I need. You guys see it? So the key here is, well, I noticed that I can factor this out. So give it a try. This is where I'm going to stop. I want you to keep trying. I gave you what to do, and let's see if you can figure the rest out. Factor it out, and maybe you need to use a definition again. Seems like some of you figured it out already. I'm going to take it up. Okay, let's do what I said. Let's factor it out. Okay, once I factor it out, I can compare again, and I'll see that, well, this is not what I want yet. But that's okay, because I have a recursive definition, right? So let's use it again. I'm going to use my recursive definition on fk plus 1. That's going to be fk plus fk minus 1. And you see that, well, those two terms cancel out. I'll be left with negative of this. Now you can compare again. You see that, well, this term should not have a negative sign. This term should. But if I factor out this negative 1, I would get what I need. So let's factor it out. that's gonna be negative of fk plus 1 times fk minus 1 minus fk squared. Again, here I used recursive definition. I should mention it. Okay, and this is exactly what I need because, well, that's my IH. Okay, so let's use my IH. This is basically negative of negative 1 to the power of k by IH, which equals to negative 1 to the power of k plus 1 as required. So we're done with it. Any question? Is this clear? If I give this to you on the quiz, do you think you can do it? Yeah? Okay, cool. Might take a while, but I think eventually you should be able to figure it out. There's nothing complicated here. All right. I have 9 minutes left. Let's see if there are any more questions. 9 minutes left. Let's talk about strong induction. I'm gonna go back and use my dominoes again. Here, I'm only gonna talk about concept, not questions, not examples. Next week we'll do examples. So let's recall using dominoes what's happening in induction, and we'll see the difference. In induction, it's basically you have two conditions. We want to show that all the dominoes will fall. In order to do that, I need to push the first one. Give it a push. That's my best case. And if I pick any random domino in the middle, any random one, I pick one of them, but I pick any of the random one. This one fall is gonna cause the next one fall as well. If you have both conditions, then every single domino will fall. That's basically regular induction. Strong induction is slightly different because, well, I still need to push the first one. Otherwise, nothing's gonna fall, right? I still need to push the first one. But now the problem is the k plus 1 domino is kind of demanding. The k plus 1, let's call this one the k plus 1 one. This domino is like, well, the k one, yes, you can fall on me, but I'm strong enough, I'm not gonna fall. You can imagine the k plus 1 is like a huge guy, and the k one is a small girl fall on a huge guy. Nothing's gonna happen. They're still gonna stay. Okay? So that's the problem. Regular induction is not gonna work because the case one falling is not gonna fall on the k plus 1 one. The k plus 1 is like, I'm okay. I don't need to fall. Okay? So that's why we need to use strong induction. Because strong induction is like, you're strong, huh? I'm gonna make everything fall in front of you. All of them fall on you. Okay, every single one of them fall on you. Then you'll fall. Okay? So maybe the k plus 1 is like, oh, I just need those two together for me. But strong induction is like, okay, I don't care. I'm just gonna make everyone in front of you fall on you, then guarantee you'll fall. Does that make sense? So your IH is gonna be different. You are not assuming this one is true anymore. You are assuming everything in front of k plus 1 is true. So from the first one to the case one, they are all true. Because using that, you can guarantee k plus 1 definitely gonna fall, no matter what k plus 1 is asking for, because it can only ask for something in front of them. Okay, that's one of the case. You need to use strong induction. That is, this one is demanding, it needs, let's say, previous two to fall together. One of the case. The other case is the k plus ones is kind of picky. The k plus ones saying, well, I don't need all of you to follow me. I don't need several terms to follow me, several dominoes to follow me. I just need this specific one. Instead of using this one, so this one follow you, I don't need it. Follow you, okay, that's okay. I don't care. I want this one specific. So k plus 1 doesn't want k, and it wants k minus 1, or k minus 2, or so on. Then in that case, strong induction works over because you make everything before following. So no matter which one you're asking for, well, I'll give you all, and you pick. Does that make sense? So in this case, you also need to use strong induction. So again, the IH is saying you assume everything before it, they are all true. So the first one to the last, to the case one. The other thing that's gonna change is the base case. Why is it gonna change? Because if we go back to the first case, when k plus 1 wants the previous two terms, for example, to push it, then what's my smallest k plus 1? What do you think? If you need previous two terms to push you, yes. The third one, right? Then this one is gonna be my smallest k plus 1. It can be. Because if you use this, there are no two terms in front of it. Or this one has 0 term in front of it. So in this case, the smallest term you can prove using induction is the third one. The first one, second one, you cannot prove them using induction. Because you cannot prove them, you have to put them in your base case. You need to check they are true already, and then you use them to prove the next one. Does that make sense? So if your recursive sequence depends on the previous two terms, and you need them, then you need two base cases. If it requires previous three terms, then you need three base cases, and so on. Yes.
So I was gonna ask if it's always two terms.
No, it's not always two. Yeah, it depends. Okay? That's if it's demanding and requires multiple terms. But as I said, there's another option, which is what if it requires a specific one? Okay? Again, you need to check what is the smallest term your k plus 1 can be. Okay, what is the smallest term it can reach? So, for example, maybe this only implies this one. For example, this one only implies this one, and this one only implies this one. So P of k implies P of k plus 2. In this case, the smallest term that you can prove using induction will be this one. Because before it, there is nothing to push them. There is nothing to imply them. In this case, you need three base cases. Does that make sense? So again, you always ask yourself, what is the smallest term I can use induction to prove? That means before this term, everything else needs to be in base case. So you'll see examples like this both. Next week, we'll do examples like that. You'll see base cases doesn't have to be two base cases. Maybe you need 5, maybe you need 8 base cases, for example. It really depends on what you need. Make sense? Any question before we go? You're all good? All good? Okay, then I'll see you guys next week.
Thank you.